Good morning, friends. Welcome to the new session. Today we are discussing about the transistor biasing. That is, there are the different types of the biasing. With the help of different biasing technique, we can bias the transistor. So these biasing techniques are base bias, base bias with emitter feedback, base bias with collector feedback, or the voltage divider bias. So let us see the fixed bias, or it is also be known as the base bias. So today we are discussing about the base bias. Okay, so in the base bias, this is the very simplest biasing technique. With the help of base bias, we can bias the transistor. And here, this is the circuit diagram for the base bias. In this circuit, we are using only one resistance, that is the RB. This RB is used to bias the transistor. Here, this is the transistor, NPN transistor, and one resistance is connected between the power supply, that is the VCC, and the collector. Okay, and this provides the collector voltage and the collector current for the transistor. And this resistance, that is known as the RB provides the input current, that is the base current to the base of the transistor. And the voltage between base and emitter is VBE, and voltage between the collector and ground is known as the VCE. And this circuit reduces the bias current changes due to the temperature variations in the VBE. But this circuit is not effective in compensating against the change in beta value. We know that the beta is nothing but the gain of the transistor. Beta is equal to IC divided by IB. If there is any changes in the beta value, then this circuit is not stable for the beta value. So this is the circuit for the base bias or fixed bias. And in this circuit, as you know, the only one transistor you use for the biasing, that is known as the base current RB. Okay, so this is the VCC. Okay, and this is the IB, the current flowing through the base resistance. This is the RB, that is the base resistance. This is the VBE, this is the ground. Okay, now let us apply the Krichobs voltage law around the input loop. And this is the input loop, because here the base current is the input current for the transistor. Therefore, this loop is known as the input loop, that is from positive to the ground, that is known as the input loop. And this is the output loop. Here we are taking the output from the collector. Therefore, this side is known as the output side. So first of all, let us apply the Krichhoff's voltage law around this input loop. And when we are applying the Kichoff's voltage law, let us go from the power supply to the ground. Okay. Now the first one is the VCC. Second one is the RB, IB. Okay. So the equation is VCC minus RB, IB minus VBE is equal to 0. Here this is the ground. Therefore, at this point, the voltage is equal to 0. This is the supply voltage VCC, and the voltage drop across this resistance is the IB RB, and the voltage drop from this point to this point is the VBE, and then the ground. So the equation becomes, the voltage equation becomes VCC minus RB IB minus VBE is equal to 0. Let us denote this equation is equal to equation number 1. Now from this equation we can write this equation like as RB into IV is equal to VCC minus VBE. Okay, we can write RB into IB is equal to VCC minus VBE. Therefore, from this equation, we can find out the value of IB, and the value of IB is equal to VCC divided by VCC minus VBE divided by RB. Suppose this is equation number 2. So here we get the value of IB, and the value of IB is equal to VCC minus VBE divided by RB. Okay, so here this VCC, value of VCC is very greater than VBE. Okay, so we can neglect this VBE from this equation. Therefore, the equation number 2 becomes IB is equal to VCC divided by RB. Okay, this is the equation for the base current. So we know the current flowing through the transistor, that is the input current, that is the IB. IB is depends upon the VCC and RB. Okay, now let us apply the Krichobs voltage law around the output loop, and here the output loop is like this. This is the VCC, this is the output loop. This is the VCC, this is the resistance RC, and current flowing through this IC, and the voltage between collector and emitter is VCE, and this is the ground. So the Krichhoff's voltage law around the output loop is equal to VCC minus RC IC minus VCE is equal to 0. Suppose this is equation number 3. Okay, now this equation can be written like this, or before that we must know about the beta. Beta is nothing but the current gain of this transistor. Beta is equal to IC divided by IB. Therefore, IC is equal to beta into IB. Now let us substitute the value of IC in the equation number 3. Therefore, VCE is equal to VCC minus beta into R. Instead of RL, we can say this resistance is RL or RC. RL into IB, equation number 4. Now, here with VCC and RL or RC, these value, that is the VCC and RC or RL, are fixed. Okay, and any change in beta means the current gain, is directly affect the change in VCE and IB. Okay, and due to that, if the VCE and IB change due to the IB, therefore the Q point on load line can be shifted anywhere, and this is the disadvantage of this circuit. Okay, so this is the base bias, this is the simplest bias, but it has the disadvantages like this. When the beta is changed, the value of the transistor voltage and transistor current is changed, and due to that the Q point is changed. So this is the base bias. This is the simplest bias, but it have the disadvantages. Okay, thank you for watching this video.